Now we introduce an important example definition. A continuous map gamma from the interval 0, 1 to Rn is called a parametrized path. So a parametrized path is a map. The image of this map, the image which is gamma 0, 1. Of course, if you like, you can denote gamma 0, 1. But we usually omit this to make the symbol simpler. Okay, so the image is called a path. So I remind you that parametrized patch is a map, while a patch is the image of this map. Okay, and the gamma 0 and the gamma 1, gamma of 1, are called the initial and end points of the patch. End points of the patch. Okay. So in the case that S is a subset of Rn, and the gamma, the image of this path containing in S, then such a gamma is called a path, a parametrized path in S. To indicate this is a path in S, sometimes we use this notation. The arrow point to S, not Rn, but S. This means that the path is contained in S. Okay. So using the path, we can define the pathwise connected, which is the central topic of this lecture. So this is the definition. A subset in Rn is pathwise connected if any 2 points in this set can be connected by a path in this set. If for any AB in S there exists a path in S which endpoint A and B. Such a path are called a path connecting these 2 points. Therefore, a set is path connected if any 2 points in the set can be connected by a path in this set. Okay, so geometrically, this set is path connected because any 2 points can be connected by a path completely contained in S. Of course, such a path need not be unique. There can be many. We can also have another path also connect these 2 points, A and B. Okay. Well, this set, if S is these 2 parts, if S is consist of these 2 parts, so this S is not path connected because this point A and this point B could not connected by a path in S. Although of course we can connect these 2 points by a path, but part of this path, this part lies outside S. Therefore, A and B could not connect by a path completely contained in S. So this S is not path connected. Okay. And some important class of pathwise connected set is convex set. So the first example is convex set. Convex set. Are pathwise connected. Okay, this is very easy to prove. Suppose S is convex, and AB is are 2 points in S. So by definition of convexity, if AB are 2 points in S, then for any t in the interval 0, 1, 1 minus TA plus TB belongs to S, belongs to the segment which endpoint AB, but because S is convex, the segment is a subset of S. Therefore, this map gamma 0, 1 to Rn, gamma t is 1 plus TA plus TB. This map is obviously a continuous function defined on 0, 1 interval and take value in Rn. Okay, so this is a continuous map, and this map is this is a path connecting AB, but it also contained in S, because this property, we know that any t gamma t belongs to S. So this gamma is a path in S connecting these 2 points. Therefore, S is path connected as we deserved. Okay, so in particular, intervals are path connected set in S because intervals in R obviously is convex. In particular, intervals are pathwise connect set of the one-dimensional Euclidean space. So intervals are path connected. A natural question is, in addition to intervals, besides intervals, are there any other kind of pathwise connected set in R? Our next proposition will answer this question. Suppose I is a pathwise connected set in R. Okay, I is a subset of R, the one-dimensional Euclidean space. It is also pathwise connected. Now we denote alpha to be the infiniment of I and the beta to be the supplement of I. Then we have the following conclusion. The first case, if alpha not belongs to I, beta is also not belongs to I, then I is the open interval alpha beta. Similarly, if alpha belongs to I, but beta is not belongs to I, then I is the half open interval. And of course, if alpha is not belongs to I, beta belongs to I, then I is half open interval. And finally, alpha belongs to I, beta also belongs to I, then I is the closed interval alpha beta. Okay. So this proposition completely described all pathwise connected subset of the one-dimensional Euclidean space. That is the set of all real numbers. Okay. So let's prove this proposition. The four cases here are similar. Therefore, we only prove the first case. We prove the first case to. You can prove the other case later.